Welcome back to physical science in the AM. Shingalka here. We're just watching the diffraction experiment on the video. So, watch this. Okay, so that's pause here. Now, we'll see a different situation here. That's with a kind of wide opening. Now, when you make the slit narrower, what do you notice about the diffraction effect, the bending effect? When it's smaller gap, it looks like it's almost circles, doesn't it? Right? And then around an obstacle, this one's harder to see on it, but kind of blocks the waves, but then you see how they come back together after? So it's blocked here, and then it's hazy, but it bends around it after a little while. Okay? I'm going to just stop this. And I'll close that actually, just so it's in the background. Okay, so then I want to see diffraction in another video. This one's better, and I'll actually turn up the volume. It doesn't show that as well, but this guy explains.
Hi, Mr. Anderson. This is J.P. Physics Potential Video 110 on wave diffraction, which is descending of waves as they move around an obstacle or through an opening. So you can imagine these are waterways here moving from left to right, and this is an obstacle put in their path. And so as these ones on the top, they just keep going and going and going. But these ones right here are being diffracted. They're slightly bending around that obstacle. If we look down here, as they move through an opening, diffraction occurs as well. We're seeing that diffraction of these waves on this side. But there's not a lot of diffraction going on.
Now, just to pause here. This shows better than what we saw at the waterways, but I want you to see an actual scenario. You see, if it went straight through, you see how that's like slight centimeter bigger because it's spreading out, right? That's the diffraction effect. As you mentioned, in this scenario, it's not happening a lot. We already know, though, that if we...
And the reason why is the obstacle is much bigger than the wavelength. What happens if we make that obstacle or that opening the size of the wavelength or smaller? We get true diffraction. So what's happening is we're bending and we get these concentric circles that are moving out from there. Now, wave diffraction is going to occur if we have an opening for water waves like this, but all waves can be diffracted, even light. So if we put diffraction grating, small slits, we can actually diffract light and break it into its different constituent parts. And so wave diffraction.
Okay, I'm going to just get out of this, but that's really, I just wanted to see those diagrams, okay? Now, we're going to take a look now at the two scenarios. Wavelength, it's a direct relationship. Shorter wavelengths, so waves that are packed tighter together, are only diffracted slightly, while longer wavelengths are diffracted more. Why? Because remember how the slit or the opening is a similar size to the wavelength to get true major diffraction. So when it waves that are packed tighter together, they don't diffract. So here's what you guys want to jot down. Draw the resulting waves. Well, here's what you're going to draw. And not as much spreading as this one in comparison. Right? And you add something to this diagram. That's why I have the whatever color box, purple box, I don't know. I'll pause the video while you jot this down. As I mentioned, though, if it's for hand in, I want you to use a ruler, and I'll supply rulers. But if you didn't bring a ruler, don't worry. Now, I said all the resulting waves, though, are two. This isn't all of them. Any wave that hits this flat part here, what happens if it was just this? What happens to these waves that hit from there? They bounce back. So, what happens, I want you to show all the resulting waves. Now, I'm using blue for these waves so you can tell them apart. That's why I don't have them on there in advance. It's hard to tell the black from the black. And you guys will be okay because your pencil will look different than the photocopy black. So, you also have the bounce back waves. Those are all the resulting waves. On the other one, they should have about the same wavelength. I'm going to just show that there's waves here that bounce back. Now, I don't have them in the exact same length.
You want to put those in?
Yes, I do. Show the resulting waves. So they bounce back on the left and the right side of it. And to show that, I'll put an arrow. Okay. Hey, guess what? I already know with the width of the opening diagram, I'm going to have the same thing happen too. Right? These waves will just bounce back. I kind of made my life easier. It took me a long time to do this, but now I don't have to redo this every time. Just snaps those waves and put them on. Then we'll talk about the resulting waves like the diffracted waves. Those are reflective. Pause. I'm going to start the recording again. Now, what we're trying to show with the second set of the comparison is the width of the opening. As the size of, and I see I've got that over time. As the size of the opening decreases, the amount of diffraction increases. Now, we have a little rule about that. The size of the opening, it's in comparison to the actual wavelength. If it's the size of the wavelength or even smaller, you're going to have major diffraction. Now, the resulting waves, we've already shown the reflected waves. That's the easy part. The new concept that's easy is that when the gap is about the same size as the wavelength, you get major diffraction. It looks like it's half circle. Right? If the gap is wider than the wavelength, you don't get so much diffraction. So finish those two diagrams, and I put this statement down underneath. My goodness. Now the statements you're jotting down underneath is the size of the opening is about the size of a wavelength or smaller. Or observable water.